Okay, because I forgot to take my COVID test, I have to do our discussion on Zoom, but that should not stop us from learning. So our first problem will be a warm-up, and let me put up the question. The question is quite long, but it is, I don't want to say it's simple, but it's doable. So okay, it is kind of long, but for part A, it's, let me try to circle the exact question before we start. So how much time does it take the person's vocal cords to vibrate through one complete cycle? And what is the angular frequency of the chords if someone sings a note of B flat, which has a frequency of 466 hertz? Yeah. So, oh, nice. Everyone logged in. Sweet. Let me get some attendance going. Ellie's here. Ethan's here. Control. Print screen. Go to Paint. Oh, by the way, sorry, y'all. Forgot to take my COVID test. Last week was hectic. The midterms made me forget. So sorry about that. File save. 11 to 12:10. All right, now we can start. Oh, Solomon just came in. Let me add him in. Solomon.
Yeah, sorry, I tried to find a Zoom link. It didn't work for a while, so I think I fixed it.
Yeah, so yeah, it's all good, Solomon. It's actually showed up. You know, it's already 90% of the battle. All right, so let me save this. Again, 11 to 10 attendance. All right, so hopefully y'all have been reading the question while I was doing this. Does anybody know how to tackle part A, which is the question I circled in red brackets? I'll start off by writing my notes. So a note of B flat is apparently 466 hertz. I did not know that. Does anybody know the definition of a period in a simple or a periodic motion?
So a period is the kind of like the time that like it completes one cycle, kind of.
Exactly.
Like,
That's
in a graph, you know?
Yep, bingo. And mathematically, as Solomon said, one complete cycle is defined as 1 over the frequency. So already we have the ability to solve for our period, which is what the question asks, and our angular frequency is 2 pi f. So yeah, part A can be solved pretty directly. All we need to do is period equals 1 over 466 hertz. And plugging that into a calculator, well, let me show this. 466 hertz is also equal to 466 something over a second. So basically this person singing a note of B flat, her vocal cords are oscillating at 466 times a second, which seems pretty crazy, but there are faster oscillations. Oh, Gabby's here, and who else is here? Cody's here. Let me retake attendance. All right. Gabby G is here. Cody D is here. Anybody else? Okay, that's it. All right. And plugging that into a calculator, your period is going to equal 2.15 times 10 to negative 3 seconds. So it takes about 2.1 milliseconds for this person to have their vocal cords oscillate 466 times a second, which seems absolutely crazy. But it's not. There are faster oscillations, as I said. Any questions on this part? I know it's pretty straightforward. Okie dokie. And then now omega, which equals 2 pi f. This one is a plug and chug, pretty much. You're gonna have 2 pi 466 hertz. And that's gonna equal 2.93 times 10 to the third radians per second. And I'll give everyone a moment to write that down or screenshot it. All right. Is it cool if I erase part A?
That'll work.
All right, cool. Oh, I was trying to be cool. All right, just do it this way. All right, part B. So part B has to do with hearing. So when sound waves strike the eardrum, the membrane in your eardrum vibrates with the same frequency as the sound. So the highest pitch that young humans can hear has a period of 50 microseconds or 50 times 10 to the negative 6 seconds. What are the frequency and angular frequency of the vibrating eardrum? Does anybody have a game plan on how to tackle this?
I think with angular frequency, there's the speed, and so it's a rate. So definitely, you'll need time t for this question.
Okay, when you say time t, are you talking about the period?
Yeah.
Yep, exactly. Yeah. So knowns, we have the period is already equal to 50.0 microseconds or 50 times 10 to the negative 6 seconds. And with our definition of period, what we want to do is isolate this. So to find the frequency, simply take 1 over the period. And then that'd be 1 over 50 times 0 times 10. Oh, yeah, 10 to the 6 seconds. And that equals 20,000 hertz. So everyone, I hope everyone learned something today. I just learned something right now. The youngest humans can hear this low of a frequency, which is interesting. All right. Any questions on this part? I know it seems pretty straightforward right now. So the second part was the angular frequency. And we know angular frequency is defined as 2 pi, because that defines a circle, 2 pi, times your frequency. So from part A, or the first part of part B, we can plug in the frequency we found into our angular frequency equation, and that equals 2 pi times 20,000 hertz. And that will give us 1.26 times 10 to the 5th radians per second. Okay, any questions on this one? Yeah, I'm pretty confident everyone is understanding this to the full extent right now. Okay. So part C. Oh, by the way, I did not skip my COVID test on purpose. And the way you guys can know is we have a physics meet and greet on Wednesday. And now I cannot go because I missed my COVID test. So the one social event that happened since March, I don't get to attend. So I am a sad puppy right now, but I'll manage. I'll manage. Okay, part C. Vision. When light having vibrations with angular frequency ranging from 2.7 to the 15 radians per second to 4.7 times 10 to the 15 radians per second strikes the retina of the eye, it stimulates the receptor cells there, and it is perceived as visible light. So for all my biologists out there, this is up your alley. So knowns, let's write that first. All right, my pen is not working. Great. All right, let's see if it works now. Okay. So omega 2.7 times 10 to the 15 radians per second. We'll call that omega 1. And then we'll have omega 2 equals 4.7 times 10 to the 15 radians per second. And what we want to do is isolate F. So I should probably put that here. The frequency range of the light that's visible to humans. So solving, I'm going to put our omega 1, so 2.7 times 10 to the 15 radians per second over 2 pi times radians to 4.7 times 10 to the 15 radians per second, 2 pi radians. And plugging this into your calculator, you will get 4.3 times 10 to the 14 hertz to 7.5 times 10 to the 14 hertz. So that's our F range, or our frequency range. So yeah. And I believe it asks for the period range as well. What are the frequency and angular frequency? Oh, so we need the angular frequency. And I kind of just gave you all the hint. So how would y'all get the angular frequency based off the frequency we just found? Oh, Sue, I saw you just popped in. I'll add you to the attendance. No worries. Anybody got a way to solve this? Or how would you get the angular frequency?
Well, isn't the angular frequency the 2 pi over f? I mean, 2 pi over f, like the period.
Close. It's a 2 pi times f.
Oh, yeah. Yeah, 2 pi
Yeah.
f.
Yeah, but exactly. Yeah, you got the right idea. And that's pretty much what matters right now. So omega equals 2 pi times f. So we plug in our frequency range that we just found. So now our, oh. So I'll do our period range, and then I'll let everyone calculate the frequency themselves, and then I'll post these online so everyone will have the answers to compare. So T range. To 7.5 times 10 to the 14 hertz. So that's the period range. So the amount of time it takes for this light to complete one cycle. And man, that's super fast. So I think 10 to the negative 15 is a femtosecond. And that's like a billion of a millionth of a second. Like I can't even understand how fast that is, but that's what nature does apparently. So imagine splitting up a second into a billion and then a million. Oh my gosh, I don't even think about it. It's gonna make my brain blow up. But last part of this question, ultrasound. By the way, how's everyone's mood today? If you're sad, I'm sad too, okay? I didn't want to skip my COVID test. Like I said, the physics department was having a social event for the first time since March, and I have to miss it now. And I don't even have a dog to play with, so or a pet
Hey,
to play with.
hey, Nate, it happens, you know? I mean, we just kind of just got to do what you got to do, you know?
Thank you, Solomon. I needed those words of encouragement for sure. Well, I always FaceTime my mom, so I'm not that lonely, to be honest. All right, ultrasound coming up. Oh, I saw that chat thing, Gabby. I feel you on that one. So ultrasound, high frequency. Oh, yep, Solomon. Okay, at least we're on the same boat. I was feeling kind of lonely for a minute. So ultrasound. So high frequency sound waves are used to probe the interior of the body, similar to X-rays, and they're used to detect small tumors or other small objects at a frequency at around 5 megahertz or 5 times 10 to the 6 hertz. What are the period and angular frequency of the molecular vibrations by this pulse of sound? So this is a cool one. If you ever go to the doctors and they do ultrasound on you, now you could kind of like give them a little smart aleck talk. Well, just kidding. Don't do that. That's a little rude. But at least you'll know how it works, you know? So frequency, 5.0 megahertz. And that's also equal to 5 times 10 to the 6 hertz. And we want to find our period of the molecular vibrations and our angular frequency. And it's pretty straightforward, so let's solve it. 1 over the frequency, 5 times 10 to the 6 hertz, 2.0. So this is the period that a molecular thing in your body takes to complete one cycle. I'm not a biologist, so I don't know the terms. And then angular frequency, 2 pi f, 2 pi times 2, oh, not 2, 5.0 times 10 to the 6 hertz. And that equals 3.1 times 10 to the 7 radians per second. And that is that one. Not the most exciting problem, but very useful in my opinion.
Yeah, that's kind of really fast if you think about it. Like that's like 20 microseconds, which is really, really, really fast.
Yeah, so that's crazy, right? Like that's what like our I don't know, our cells in our body are like oscillating at. So yeah, that it's kind of weird to think about. It puts me to sleep for sure. All right. So now, oh man, I spent so much time on this problem. That's okay. So 4.16 is a simple harmonic motion problem. Has Professor Rudy went over the concepts of this yet? I'll take the silence as a no.
Yeah, no.
Okay. Insert picture from file 14.6. Okay. So I'll let everyone have a second to read this. And if you have a way you think you can figure it out for part A, feel free to, blurt it out. Okay, so has anyone thought of how you can figure out part A? So if the amplitude is doubled to 0.18 meters, how long does it take the block to travel from 0.18 to 0.18 meters or negative 0.18 meters? So essentially they're asking for the period. Let me draw a free body diagram. So if this is our equilibrium position, call this x equals 0. And it travels at negative 0.180 meters. And let's say it also goes here at some future time. Any ideas, or should I just start solving it?
An idea I have is like the properties of waves themselves. And well, you have amplitude, you have the wavelength lambda, and then you have, the distance in between each time the wave oscillates. So I guess using some of those properties can help find frequency due to wavelength and, how long the wave is and how long it completes each cycle and stuff like that. Right?
So bingo. So Solomon, if you wrote all that out, I think you would see this is kind of a curveball question, but if you wrote this out mathematically, like you would see why the answer is the way it is. So period is 2 pi over omega, and this is for simple harmonic motion. Period can be defined as this guy. And also because, let me be more clear. Omega equals 2 pi f. And if you take the inverse of f, 1 over f, that is, trying to do my math in my head. Yeah, oh yeah, 2, yeah. Which is also the period. And from this equation, oh, I just did it. So does this equation depend on amplitude at all?
Not necessarily.
Oh yeah, it doesn't. So the period, if you were to double the distance this block travels, is going to be the same. So the time it takes to make a period is going to be the same. So t, same as I feel like that's a little hand wavy of an explanation. Is that kind of clear? The way I understand it is through the mathematical definition, just because amplitude isn't in this equation. So that's how I always understood it.
I guess the question I have is like, why did they give us the amplitude for that reason? Then if it isn't involved in this equation at all.
Yeah. So I think the point they were trying to make is that the period is not dependent on the amplitude in simple harmonic motion without friction and without air resistance and all that. Does that sort of answer your question? I hope.
Yeah, it makes sense now.
Okay, sweet. So now for part B. So for part B, it was a little confusing just because I read it wrong. So let me explain this. So for part B, it wants the time it takes. Well, let me read it first. Yeah, so basically it wants the period from x equals 0.09 meters to negative 0.09 meters, but I didn't know that they meant within this interval. So I did the whole problem with this as 0.09 and this as 0.09 when they actually wanted like this. So what's the time it takes for the block to go from here to here, to here, to here, to do that period? Is that clear? That's pretty much like the main. If you understand that part, then you're golden. All right, I'll take the crickets as a yes. So does anybody know the displacement equation for simple harmonic motion? Like x equals, any idea? All right, well, since Rudy hasn't gone over this, I'll write it out. So simple harmonic motion, displacement can be described as the amplitude times your cosine times your angular frequency minus your phase factor. And your phase factor is basically just how much something is shifted, right? Say like you have a football and it's put at 10 meters instead of 0, sort of like what the phase factor is saying. But in this problem, I think it says it's not dependent on a phase factor.
Nate, what's the W or the omega t again? Sorry.
Oh no, it's all good. Yeah, omega is the angular frequency, and then time is the seconds. So yeah, omega or angular frequency can be thought as let me do this, as velocity, and velocity is x over t, and then this part here. So then these two units matches up. Does that answer your question, Sue?
Yeah, thank you.
Cool, sweet. Erase that. All right, yes. So basically, this equation gives you, like, it describes the position of your object if it's going through simple harmonic motion. All right. So with no phase factor, we simply have the amplitude times your cosine, omega t. And that's pretty much all we're going to need for this problem. So now solving. So our period is going to be 2.7. And I think we solved that. Wait, it's given to us. Yep, that's given to us. I'll put this in parentheses, given. And this is for so this is the period between at the 0.09 meter mark and the negative 0.09 meter mark. Now, our situation is, this is where I got confused. Our situation is the amplitude is doubled to these guys to 0.18. So now our period is 5.4. Our period doubles because our amplitude doubled. You can go through the textbook to find that out. I just don't have time to go through the nitty gritty right now because I have 17 minutes, or did I do the math right? Something like that, yeah. So that's our new period for the doubled amplitude. Oops. I'll put 4 doubled amp. All right. So basically, so we don't get lost in the forest among the trees, what are we trying to solve again? So basically, we're trying to solve for half the period. So how long does it take for this block? So if this is the period, going here and here, all we want is this length. How long does it take for the block to travel half the period? I hope that made sense. Okay. So to do that, oh yeah, go ahead.
So you said the amount of time it takes for half the period. So is it half the cycle, I guess, right? Is it half the cycle?
Oh yeah, that is true. It is half the cycle, but since we're only paying attention to this position, it's not going to be exactly half the cycle if you're trying to solve it in a very quick way, like taking just half of this, right?
Right.
Yeah. So this is for the 0.18 meters. So yeah. But yeah, good thinking. Always try to think of a quick solution if you can. So to solve this, we're going to use the angular frequency equation because we need to plug it into here in order to get the distance. So we will do omega 2 pi over the period, 2 pi over 5.4 seconds. That's 1.16 radians over seconds. So now we could use our simple harmonic displacement equation. So for T1, we're paying attention to the 0.09 meter distance, but we know our amplitude is doubled. So we're going to use the 1.08 meter amplitude times cosine omega t. We just found that to be 1.16 radians per second. And we want our time 1 it takes to reach this distance. So yeah, we're trying to solve for the time it takes to get to the 0.09 meter mark if our amplitude is 0.18 meters. Is that clear? Because this is basically the physics right here. If you know how to isolate T1, you understand the physics. And now it's math from here. Okay, so I'll go through this one kind of slow. So we will have 0.09 meters over 0.18 meters cosine 1.16 radians per second times T1. Yep. and then doing some math. No, it's half of it. And cosine 1.16 radians per second times t1. Yep. And then now I'm going to take inverse cosine of 0.5 seconds, which equals 1.16 radians per second times t1, because we undid the cosine function with our inverse cosine. And now isolating t1, cosine 0.5 seconds, 1.16 divided by 1.16 radians per second. And plugging that into your calculator, you should get 0.903 seconds. That's your T1. Is that clear? I hope.
That made sense.
Cool, awesome. So now T2, it's the same process, so I won't go through it again, but there is one little caveat. It's going to be negative 0.09 meters. That's careful. It will give you a different time. And your amplitude is still the same times your wave or trig function, cosine, and same frequency. It's simple harmonic motion times T2. And isolating T2, you get 1.806 seconds. So now we combine our T2 and T1 by taking the difference, and that will give us the time it takes to travel, just like, so if this end is the starting point and the end point, the time it takes to travel just here, not here and back for the period, just half the period. So we take the difference of these two. And interestingly enough, you still get your T1. But it's best to go through all the math before making assumptions. Okay. So did this problem make sense? Because I guarantee you, Professor Rudy is going to ask you a simple harmonic motion problem on the next exam. That's like guaranteed.
We haven't gone through it in class. Like, is this from chapter 14?
Yeah, chapter 14.
Okay, I think that we're just finishing up rotational motion still.
Oh, geez. Isn't your exam pretty soon? I saw he put up the training exam.
It's on Thursday. Yeah, we haven't gone through. We're still haven't even gone through like gyroscopic motion or anything.
Okay, I take that back. Maybe he'll give you one problem, and it might just be on the basics of simple harmonic motion. Because that'd be unfair if he gave you a bunch of stuff on simple harmonic motion. So yeah, base your studying off the training exam, and if you ever need help, feel free to schedule office hours with me as usual. So, all right. 434. I'm tempted to do this one, but now I want to make sure everyone knows what to know for the test. All right, I'll go through this problem. It's a block on a block problem, and the block is attached to a spring. All right, so here's our situation. We have a big block of mass M and a little block on top. And in between the blocks, we have the coefficient of kinetic friction or sliding friction. I'll denote it mu s. Oh, that looks like an N. Oh, that looks like another N. That looks like a third N. Sorry, I'm a perfectionist sometimes, or a lot of the time. Okay, there you go, mu s. Oh, and there's a spring. So find the max amplitude. I can't spell today. Find amplitude max such that blocks will not slip. Okay, so this will be the last problem we go over today. There is one more problem, but as usual, I'll put all of these online. And if you have a question on any of these problems, always feel free to email me or schedule office hours. I'm really not tripping. All right. So knowns for this problem, I have to give you that. In simple harmonic motion, your acceleration max is k over your mass total times your distance. But in this case, amplitude is your distance, right? Because amplitude defines how far your object is moving times your amplitude. Okay, and for the next one, if we don't want the blocks to slip, what do we have to know about the max acceleration? So I want to give everyone a minute to think about that. And if you don't understand my question, always feel free to let me know. So the max acceleration of the lower block, what restraint do we have if we want it so that it doesn't slip from the top block M?
Is it friction?
Yeah, friction, exactly. So the max acceleration of the lower block can't exceed the max acceleration of the top block, which is based off the mu s, because the frictional force is mu s times your normal force. So yeah, you pretty much had it, Solomon. Max acceleration of the lower block can't exceed, I'll do this, Fs equals mu s, so you know there's friction times m of top block. Yep. And from here, it's a derivation, pretty much my favorite. So now we will solve. So our frictional force for the top block is going to be the coefficient of sliding friction times your normal force. And from your chapter 1 and 2 days, that is also going to equal mu s times mg, because that's what normal force is. Or it's equal, your normal force is equal to your weight. And then we use the superposition principle. And that's going to equal your coefficient of sliding friction times your weight. And that's going to equal MA. That's kind of redundant. And we want our amplitude, right? So we're going to need our acceleration, because so we don't get lost in the forest. It's K M total times our amplitude. And we're looking for this. So right now we're trying to find this, our acceleration max. And our acceleration max will be the max or the frictional force of our top block. So A is equal to mu s mg over m. Yeah. Oh, the m's cancel. So what's going on? Mu s times g. Now, can anyone think of a trick right now for A max? What would I put in the mass box? Okay, so it'd be our bottom block plus our top block. And then that is, we're like treating the whole thing as a system. So basically they're moving together with the same frictional force that the top block is applying to the bottom block. Yeah. So now working it further, we know mu s times g is our acceleration that we found previously, times k, which is our spring constant. Oh, and this is going to turn out to be in a variable form. So don't be scared if there's no numbers. Times your amplitude. And yeah, now we solve for our amplitude, which is going to be mu s times g m plus m over k. And this is your max amplitude, which is what we wanted to find. So I think Professor Rudy might ask you, like, find the amplitude in terms of mu s, m, big M, little m, and k, and g. And you're going to have to get to this answer based off just these notes right here. That's what I remember from fall 2019. So he might not put the same exact thing, but it's nice to always be prepared, right? Okay. I think that's it. Any questions before I end the session? And I'll post these on tonight, these solutions. So. All right, everyone can go and enjoy the week, and yeah, take care and keep your spirits up. And good luck on the test this Thursday, right?
Yeah, it's this Thursday.
All right, I'll say a little prayer for y'all, so good luck.
Thanks so much, Nate. Have a good one.
No problem, Solomon. Take care.
Thank you.
That's it.